started. I think I'm going to have the third test 2 weeks from, how did that work out? Is it 2 weeks from today? I think it was. I believe I did have it for 2 weeks from today. So yeah, I'm fairly certain. So that means the review session will be on that previous Tuesday. And next week, I'll cover the next 2 sections and then have another homework review session on next Thursday, like we're doing for this week. And so by spacing everything out like that, everything will work out. At least as I have everything projected, everything will work out perfectly.
That's the fifth, right?
Yes. So the next, the third test, which is unproctored, you take it on your own. So that'll be on Thursday. And I was thinking about either having it available for you to take on Thursday or Friday, but we will have class, or we don't have to have class, but I make it available one day. So if there is a collective preference, we'll lean more in that direction. Thursday or Friday, that means we will have class on Thursday. So for Dennis, so we could have it 2 days, but we have class, or we don't have class, but it has to be on one day. Might be something to keep in mind. If I don't get any preference one way or another, I'm just going to do which one seems more convenient to me. So besides for that, personally, I'm leaning towards no class, one day to do it.
Yeah, I'd rather do that too. Yeah, I usually work Fridays, so.
Okay, well, we'll figure it out. So the syllabus doesn't say anything one way or another, so I can kind of pick what I want, but I can also be a little bit accommodating. Well, we'll figure it out. We have 2 weeks. Aim on it to be Thursday though, but no class. That's the goal so far. So, besides for that, test 2 weeks, review session, the class period before. Yeah, I suppose let me stop rambling and actually start talking about some of this stuff. Okay, so last time in class, we started off talking about the things from the section on fundamental identities, which was using algebraic principles and these formulas as well to simplify various expressions, trigonometric expressions. And I felt that since this section is a little dense, as I mentioned later after I'm done talking about everything, which shouldn't take the whole class period, I'll just have a homework review session, which doesn't mean I'm going to do all the problems, just means you can work them out. I'll give hints here and there, but you can have the class period to figure those out. I was hoping Blake would show up. I don't know. Is Blake in here? Wherever he's at. I was hoping Blake would show up. Figured I'd get him to come up and do a few problems. He's not here. Oh well. But yeah, we went on to talk about as well. I talked a little bit about the sum and difference formulas for cosine as well. And I did examples 1 and 2 last time. I'm going to do example 3, which will be very similar to example 2. So the goal is to find the exact value of this, which does not mean throw it in a calculator and see what the decimal equivalent is. That is cheating. I mean, it's more interesting to find the exact value. It's more precise anyways. So the way we go about it is by utilizing one of these 2 formulas. These are 2 distinct formulas, and we need to figure out which one we can use to our advantage. Now, example 2, it's fairly easy to figure out because, well, what do we know exact values to? 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. These are some of the special angles that we know pretty much offhand. So notice these are in degrees, and yet our problem is given to us in radians. So what I normally do, I like to quickly go ahead and convert this radian to degrees. So hopefully you remember how to do that. You need to get rid of the pi. So it makes sense that pi goes in the denominator because the pi's cancel. And so whatever 11/12 is of 180, probably like 330 or something, or maybe 345. Oops, 11/12 times 180. Oh, I'm way off. Never mind. Okay, forget that. It's 165. 165 degrees. Okay, cool. So really what we're looking at is not what we started off with, but we're going to go ahead and look at something that's a little bit easier to manipulate, 165. And so you might be looking at this. If you do remember from the last class period, I was saying what numbers add or subtract to give us the 165. Well, really, I mean, the two largest numbers on here, well, you can add 90 to itself and get 180. That's too large. And then the next two largest ones are 90 and 60. You add those together and you get 150. So you might think, all right, that's interesting. How do we get 165 then? Well, there are more special angle values. I mean, there's the quadrantals in general. So does that help us? 180 degrees and 270, 360. There's these as well. Well, is there any way to add or subtract any combination of these numbers to give us 165? I mean, there's that 5 there, so I'd imagine if anything 180 minus 45, but that still doesn't work. You might think, all right, well, what gives? What's the trick here? Well, we have even more special angles, and we can figure those out because of reference angles. So we have more special angles. We generally tend not to identify them. We more so look at their reference angle. So, for example, normally when I see the 5 right here, I think 45 degrees is going to be involved. So the 45 degrees, because all of our other special angles here, none of them have a 5 in the single digits place. So a 5 is going to pop up somewhere, only for the 45 degrees. So let's see, if we used the 45 degrees, what options do we really have? 165 degrees, we could subtract 45, that's 120. Or if we added, it's 210. So you might look at this, oh, there's Blake. So you might look at this and think, all right, well, the combination of numbers that we can put together are I'm going to erase this and write it in another way. So how do we get 165? We could add 120 plus 45 and use an addition formula, or we could subtract 210 to get 165. So that means that the second angle that we have doesn't immediately look like a special angle. Those two angles that we're using do not belong here. But actually they kind of do, because of reference angles. Remember that super important thing from the very beginning of this class. So it turns out that the reference angle of 120 degrees, well, the reference angle of it is 60, which is up here, which means 120 degrees is a special angle as well. And what's the, so just to convince you all of that. So 120 degrees would be about right here. And then how do you find the reference angle? It would be right here, which is just the remaining 60 for what it takes to get 120 to 180 degrees. So really, 120 is a special angle. It's the reference angle of 210. It's 30. So 210 is also a special angle. So really, what I can add to this little table of values here so the nice generalization is we consider any number such that special angles, the quadrantals, 0 degrees, 90 degrees, 180, we also consider 30 degrees, 45, and 60. And any angle whose reference angle is 30, 45, or 60. And this is going to be relevant in the next section as well. Actually, the next two sections. So really, these are our special angles. So with this motivating factor in place, let's back up a bit now. So now that we have a larger lexicon of values to choose from, we need any two numbers from that table to either add to give us 165 or subtract to give us 165. Since we see that 165 has a 5 in the singles digit, we know that 45 is pretty much going to be one of these values. And you could use algebra to figure out the other value. And so we can either add, we can use the addition property or the subtraction property. So if we use the addition property, what adds to give 165, we figured that out before, is 120. And we can use 45. So 45 is a special angle because it's explicit. It's right here. 120 is a special angle because its reference angle is 60. So it also is a special angle. That's why we're allowed to use 120. And the reason I'm emphasizing this so much now is that this is going to come up in the next two sections as well, as we learn to take a number and break it up as a sum or difference of these special angles here. So, or you could have picked 210 degrees minus 45 degrees. You will get the same answer either way. Because both of those, 210 is a special angle as well. So, with this being said, I'm going to choose the addition one for no particular reason. You could also pick the subtraction one. So 45 degrees plus 120 degrees. And as soon as we find that addition, now we know we can use the addition formula that's at the top of this page. The addition formula is right here. So we put some cosines next to each other and we flip the sign. So it's cosine of 45, cosine of 120. And then it says if we're adding, then we put a subtraction sign here. And we do the same thing with sine. And the reason why we call these angles special angles is because we can figure out the exact value of each one of these. So let's turn to the calculator. Hopefully your calculator is in degree mode because these are a bunch of degrees. Cosine of 45 degrees is the square root of 2 over 2. Because I told you to recognize that decimal, the 0.707. All right, what about cosine of 120? I get negative 1/2. All right, I see a minus sign. Now sine of 45 degrees, square root of 2 over 2. I noticed I made a mistake as well. That should say sine. That should say sine. Make sure that says sine. My fault. And then sine of 120 is 0.866, which means that's the square root of 3 over 2. That's one of those other decimals I told you you have to know. Now simplifying this, hopefully you remember how to multiply fractions together. It's going to be negative square root of 2 over 4 minus square root of 6 over 4. When you multiply two square roots together, you multiply what's underneath the square roots. And they may write it in the book as one combined fraction.
Why doesn't the square root of 2 get the negative?
What's that?
Whenever the way the book would say it, why doesn't the square root of 2 get the negative?
Oh yeah, I left off the negative. Sorry.
I thought it was just a...
Yeah, nope, that's me. That's all me. There should be a negative in front of the square root of 2 because there was one in the front here. So my fault. Let me see what how the book words this. Because if the book does not say to simplify, really, you might be able to avoid some steps. So let's see what the book says. So find the exact value, do not use a calculator. See example. Yeah, so the book definitely simplifies because it likes to show off. Really on the homework, what I'd at least like to see is at least one algebraic progression, one algebraic simplification to at least clean this up a little bit. Because that is technically fairly simplified in terms of at least making things simplified term by term. Now you can go ahead and take the additional step and make it a singular fraction. And I could ask that on the third test to express your answer as a single fraction as opposed to two or more fractions, which would force your hand at providing the final answer as such. So maybe that's something you want to mess around with. I'll talk more about that during the Unit 3 test review. But really, on the homework, I'd rather you not leave it in this form, but instead leave it in the form that I have here in blue. Kind of my preference. So the thing in blue is what I would like to see on your homework for this section, if you're doing an equivalent problem. Does anyone have any questions about this?
So unless you specify on the test, we can leave it as the form you want to see on,
Leave it as the,
as two instead of just.
yeah, that's fine.
Okay.
Really, even if on a test I said make it a single fraction, if you got to this part correctly and didn't simplify it, take off like half a point. It's not, if you make it that far, then you pretty much know what's going on. And a half a point, that's, I don't know, it's really not a big deal. If you think about it as, I'll just take the L, I don't care about simplifying, it's a half a point. It's not a big deal. But we'll see more stuff like this because in the next section, I'm just going to skip ahead right fast. In the next section, there's these formulas for sine, and it's very similar. You can see problems that look just the same. So we're going to be doing this stuff again next week. Let's look at example 4. And this one is it's a little bit of a trig or fundamental identity along with using the formula. So it's pretty much a combination of this section and the last section. And it wants us to prove, so hopefully, well, we haven't really used this much, but this is one of those co-function formulas from way in the beginning of this class. And now, in the spirit of the previous section where we were proving things, here we're going to prove this using the cosine difference identity, or the formula. So what they're wanting us to do is use this formula, I'm just going to rewrite it. This is verbatim the formula from up top. So all I did was just rewrite the formula from up top because they want us to take 90 degrees minus theta, and they want us to do stuff to that side and simplify it to get sine of theta. All right, so we're going to use this formula up here. So here all I did was state the formula. And now I'm going to apply that formula directly to cosine of 90 degrees minus theta. Now, it seems like here 90 is A, and theta as a variable is B. So every place I see A, I'm going to put 90 degrees. Every place I see a B, I'm going to put theta. So I'm taking the left-hand side of the identity, taking that left-hand side and just expanding it out, seeing what I can do with it. And so I get cosine of 90 degrees, cosine of theta, plus sine of 90 degrees, sine of theta. So this could be simplified because we know what cosine of 90 degrees is, right? Do we? I hope we do. What is cosine of 90 degrees?
Zero.
It is 0. Cosine of 90 degrees is 0. Sine of 90 degrees, it's 1. So that's convenient because
0 times cosine is
yeah, 0.
obviously 0.
Yeah, 0 times cosine of theta, I'll simplify that in a second, plus now 1 times sine of theta. So if we,
0 plus 1 times cosine theta is just 1 times cosine theta, which is just sine, or not cosine, but sine. I don't know. That was confusing.
you're just saying a
So
bunch of
basically
trig words at
0.
this point.
Yeah, it's basically 0 plus 1 times the sine of theta.
Yeah,
And then 1 times the sine of theta is just sine of theta.
so in other words, this term just disappears. Because 0 times anything is 0, and you're adding 0, which doesn't do, well, squat. So you're left with sine of theta, which, hey, that's what we were trying to get. So we just proved a formula by using another formula. So this is the kind of stuff that you do in theoretical math a lot of times. You make some sort of, you collect a bunch of data about the equivalencies between two things, or you try to work out a function. You get a bunch of data about the function, and then you try to conjecture some sort of formula for what this function looks like, and then you try to prove it like this. Now, sometimes proving things is condensed to a few lines, or sometimes you can write a master's thesis about it. Some things are easier to prove than others. I wish my thesis was this easy. It is pretty fun though. It's like a little puzzle. So we have now proven that cofunction identity, which I think is pretty cool. Okay, let's move on to example 5. Unless anyone had any questions about that last one. So example 5, find the exact values of cosine of s plus t and cosine of s minus t. And then they give us some stuff about sine. And then they tell us stuff about s and t. Okay, this is kind of interesting. So this problem seems a little oddly worded, I suppose. So if anything, they want us to figure out cosine of s plus t. We'll look at that one for now. We'll look at cosine of s minus t later. So what is cosine of s plus t? What can we do with that? Wait, we have formulas. We have an addition formula. What does the addition formula say? We can rewrite this as cosine of s, cosine of t, minus sine of s, sine of t. That's straight from the formula on the previous, is it the last page or the page before? The last page. That just comes straight from the formula. And so now what this says is, in order to complete this problem, we need to know four things. We need to know cosine of s, cosine of t, sine of s, sine of t. Well, wait a minute. We already know two of these. Two of them are already written. Is this a joke? I mean, are they just giving us the answer here? Well, we don't know cosine of s. We don't know cosine of t. But we do know sine of s because they gave it to us. And we know sine of t. Really, that's just plus 2 over 9. So we have that so far. Of course, negative times a negative is a positive, so that's why it's positive, 2 over 9. But now we need to figure out cosine of s and cosine of t. The question is, how in the world do we figure those out? Well, let's try to figure out cosine of s. Well, they gave us that sine of s is 2 over 3, and then they tell us that s is in quadrant 2. How is that helpful?
No, it's positive or negative.
Well, yeah, ultimately so. We need to figure out, so if sine is 2 over 3, well, that tells us that sine is a positive number. When is sine positive? That's in quadrants 1 and 2. So then they're saying, all right, well, let's ruin the ambiguity. We're going to be in quadrant 2. So let's just draw something. In fact, I'm going to do this. I'll put this one over here. I'm going to call this the S angle. We're going to do a similar thing for the T angle. So it says that this angle is in quadrant 2. So I'm going to draw an angle in quadrant 2. This angle is S. Now if we triangulate, then it's saying that sine, which is opposite over hypotenuse, is 2 over 3. And then we could figure out the last side using Pythagorean's theorem. That would say 3 squared minus 2 squared is equal to the remaining side. So the x is the square root of 9 minus 4, 5. And the 5 is going to be negative because it's going to the left. So that means cosine of s, according to this triangle that we just drew, is negative square root of 5 divided by 3. It's a good thing we're doing something super incredibly similar to this to figure out cosine of t, in case you missed any of that. So if you missed that, let's do the same exact thing, but for the angle t. Because our motivation is, all right, we found cosine of s, and we need cosine of t. All right, so what do we know about t? Well, we know sine of t is -1/3. All right, when is sine of t a negative number? Well, that's normally in quadrants 3 and 4. Then it goes on to say t is in quadrant 4. So for the t angle, it says draw the angle in quadrant 4. So this is angle t. And if we triangulate, it tells us that sine of t is -1/3. So sine is opposite. So I'll put just the numbers first. It's opposite over hypotenuse. And then where does the negative go? It goes on the 1 because that segment is going downwards. So it has to go there. And the hypotenuse is never negative either. We can use the Pythagorean theorem to figure out the missing side. This would be 3 squared minus -1 squared is the missing side squared. So x is the square root of 9 minus 1, which is 8. And so the cosine of t, now that we have that missing side value, is square root of 8/3. Because it's adjacent over hypotenuse. We just found that adjacent is the square root of 8. So square root of 5 times square root of 8, well, 8 times 5, 40. So really, that's the answer I'm looking for. I went ahead and combined it as a single fraction. The book might combine it as a single fraction, and just so you see where that's coming from. But what I have boxed in, that's what I'm okay with. Unless I say combine it and make it one fraction, which then the lower answer would be preferable. The sad news is we're not done, but we're very, very close. Because all of this was trying to figure out s plus t, but we still have to figure out cosine of s minus t. But we already know all the pieces. So really, it's not too much of a step further. So we're still trying to figure out cosine of s minus t, which the formula tells us that this is cosine of s, cosine of t, plus sine of s, sine of t. And we already know all of these values. So we know all of them. We found cosine of S to be negative root 5 over 3. Cosine of t, we found that to be the square root of 8 over 3. Sine of S times sine of t, we simplified that already to be 2 over 9. Or you can plug them in individually, you would get the same thing again. Actually, no, you wouldn't. I'm sorry. Okay, maybe I should be careful with that then. I'll plug them in one at a time. 2 over 3, negative 1 over 3. Negative square root of 40 over 9 minus 2 over 9, which is negative 40 minus 2 over 9. So the only difference are the signs. One sign changes. Instead of plus 2 over 9, it's minus, because the formula only changes by a middle sign. But what I have boxed in, that would be preferable for the homework. If on the test I asked for a single fraction, then I would want the form that the subsequent form. Do you think you can recreate all those steps? Well, that's all I have for this section. The homework review is not going to be a review where I just do problems from the homework left and right. But instead, it's going to be where you can all discuss problems. And if you would like my most immediate help on something, you'd have to come up here and work it in front of everybody. See, doesn't that sound fun?
Yeah.
So let's see. So I guess before I continue any further, this section and the previous section, both of these homeworks are due next Tuesday. So next Tuesday, this homework and the section before on the fundamental identities, those two are due together on Thursday or Tuesday, next Tuesday. But we're going to spend the remainder of class time going over some of these problems. Okay, so let's see, what are some of these problems? So I'll look at this section. Kind of curious. 9, 13, 17, 18. Okay, the first 4 shouldn't be too bad. 50 should look familiar. 52 is one of the ones that we just did. 67, it's interesting, 70. Okay.
So for the section before that, they've got a lot of like 1 through 7, and then like 39 through 44. Like, are those going to be like more simple questions?
Yeah, they're more simplistic. In fact, I'm looking at them now. They're kind of, so let's see. 1 through 7, it's match this one to that one. And then 6 and 7 are just, those are problems you can answer really quickly. 39 through 44, same idea. Match this one to that one. You will have to expand them. Let's see, which one or ones would be the most crucial to look at? So we got 30 minutes here. It's a lot of time. Blake, are you itching to try any of these problems in front of everybody else? Rebecca, are you wanting to do some problems in front of everybody? Logan? No. That problem we just did, would it be nice to see another example of that problem? The one we just finished? Because that is one of your homework questions. So which one is that? Also, 70, let's take 70 out. 70's gone. I remember that one from last semester. Wasn't a big fan favorite. Number 70 from that homework's gone. That one did not end up going too well, so let's ignore that one. So 70's out for the sum and difference for cosine section.
Yeah, I assume if we did like, on 5.1, it probably would not be 1 through 5.
Nah.
But 1's pretty simple.
You want to come do 52 on page 219? That's the one we just did. They give two cosines.
I can try it out.
You try it. Cool. What is this? So, same thing as before. I sure didn't write anything down. I tend to do that sometimes. Page 219 might be different because I do have the instructor's copy. I don't know if it is different or not. I have the instructor's. Oh, okay, cool. Never mind. Where are those numbers coming from?
That's -8/17, and then 3/5, -3/5.
Well, I mean, I can read it, but where are those numbers coming from?
Cosine of S is negative.
I understand that as well, but you're kind of just placing numbers in arbitrary spots.
So you want me to go and write like cosine S and all that first,
That
and
would
then
be
substitute
nice.
it?
That would be nice. The calculator to the right, that will supplement you in your arithmetic progress.
Oh, well, yeah, I was trying to like first convert them both, like, but I could just make it one fraction
I
instead.
mean, 8 times 3 is 24, 17
Yeah,
times
yeah.
5 is 65. Or, not
Yeah,
80.
yeah.
Plus the 24 over 85?
Yeah, 24 over 85.
Okay, so 24 over 85.
See, yeah, I was making that way more complicated. I was like confusing myself.
No worries, just go ahead and start finding sine of x. So quiet while doing this. Maybe use a different color to really differentiate structures from numbers.
Alright. So,
Yeah. Use like a red or something that tends to pop.
there we go.
Why is the -8? Not saying you're wrong. Why is the -8 where you placed it at?
Because it's cosine, so that's the adjacent angle.
That's right. It's the adjacent angle.
And now it was.
Oh, that's such a pet peeve. Put -8 in parentheses. There you go. So I'll go ahead and solve that for them right fast. 17 squared,
289.
289.
Alright, so
I'm
then.
guessing that's for the whole thing.
Oh, no, sorry, that was just 17 squared.
Oh, that's fine.
So then just. So like 225.
The answer's gonna be 15, so I guess I'll just run the fun there. I'm pretty sure it's 15.
Yeah.
There we go.
So. Now you figured out opposite. Cool.
And then I can go ahead and do T now, or do I put that in?
Go ahead and do T. You can just do them both at the same time.
Not very proportional, but it's all right.
Remember, you can rest your palm on the screen.
Okay.
That tends to help with stability. It's a real game changer.
And then it's adjacent again, so it'll go there.
Just put that X's for. I'm hoping everyone can figure it out from there.
All right. And then
All right, don't erase anything. You're in one of those rare situations that two wrongs make a right. 15 should be negative, 4 should be negative. It's a downward direction.
yeah,
So what happens in this problem that the negatives would cancel out.
yeah.
So, but
Just
Yeah.
put negatives in both, and then
put
No.
negatives in both and then,
yeah,
which I mean, that's minus negative 15 over 17. Because the first negative there is from the formula.
yeah. So this would be
That should, yeah, exactly. So it's just, so you would have had two wrongs to make a right, and
Yeah.
if I saw that on a homework test, I'd probably don't. Like, the smallest little point,
yeah.
quarter of a point, and say, that job.
I keep not flipping the sign and change that.
So here you can actually really simplify it. You don't have square roots and stuff. You can actually combine these fractions together.
So it's gonna be
So it's 24 minus 60.
Yeah.
Whatever that is. Negative 34, or 6 rather.
36.
Negative 36. 35. Cool. And we'll assume that everyone can do the same for the cosine of s minus t.
so we're
What do you think? Work that one, the s minus t part out or nah? Because we found cosine of s plus t, but it also wants cosine of s minus t. Can you work that one out, or can you all figure that out? I mean, really, the only difference is 24 over 85 plus 60 over 85. That's the only difference. But, all right, cool.
so, and then you want me to just put up here like because that's what that'd be, right? 24 plus 60, 84 over 85.
Yeah. That would be right. I just want to make sure everyone knows how it's right. I'll take it from here. I'm leaving it to you all to put work in between. I'm also going to make this legible. Sorry, Blake.
Yeah.
It takes a little bit of getting used to, so you're a good sport. Cool. I wonder who left. Let's find out. Okay, I know who left. Cool. I don't know if you all know, Google Meet sends me a nice list of how long you've been in the Meet sessions. It just started doing that like a few weeks ago. So that's pretty cool. So now I know. But pettiness aside, that is 52 from that homework. Any questions? No? Cool. Awesome. Let's look at another problem. Let's see. What's another one that's interesting? Well, Blake, you did a great job. All right, so I took out 70, 67 is 1, 50. 50 is just like, in the same section that is. 50 is just like example 4, so I'm gonna leave that one alone. That one shouldn't be too tricky. Maybe 67. Yeah, let's look at 67 from the same section. It'll kind of knock out 2 birds, 1 stone, maybe. It's also, kind of an identity thing, so. So same section, same page, 67. So we're proving this. So that's how you interpret this. This is something we're seeking to prove. Well, like I said, I'm not planning on doing this one. Is anyone brave enough to come up here, or do you want to just kind of shout out? And I'm open to whatever. I mean, if anything, I'll start it off. Take the left side, and we're going to do something to it. And hoping it ends up looking like the right side. What's that? With a reciprocal identity, how would you apply that? And I see an addition within a cosine.
That be, you make it the pi over 2a and the xb.
Yeah, there's an addition within the cosine. So reciprocating would be, make it pretty nasty. I wouldn't want to do that. So
it's cosine pi over 2 times cosine x minus sine pi over 2 times sine x.
I'll leave it at that.
So radians too, so if you have a calculator, it better be in radian.
Yeah. Well, you also know what the end result better look like.
Yeah.
So I'll leave it at that, so we can look at other problems. But I think that's a pretty helpful hint. That should be more than enough. Besides, there's a homework problem there's a problem from the notes that we pretty much did this exact thing for, except it was degrees. And shoot, it was even, wasn't it 90 degrees? It was 90 degrees. What's pi over 2? Just 90 degrees. Okay, so I'll leave it at that. So that's 67. I gave a hint. When you turn in the homework, if I see your work here, I'm gonna laugh and put a big red X through it. So don't do that. Actually put work there. There. That's 67. That's a hint for 67. That is not completed. So you have to complete that on your end. All right.
That's where you start and where you want to go.
Yeah, so. Let's see, what else is there? All right, we talked about 52, we talked about 67. Number 50, I think that one kind of already looked at. Nine and 13. Should I do either 9 or 13? Or should I look at the other section, the first section? I agree, I should look at the first section. Those are probably a little bit more difficult. I'm gonna hope you can figure out the rest of these, because historically, students have been able to figure those out more than these problems. So, we're going back, looking at fundamental identities.
And I mean, we're not really gonna go over the, matchings, are we?
You're really hung up on these matching ones, huh?
Well, I mean, 1 through 7, like those are part 1 probabilities, those are pretty easy looking.
So you want to go through 39 through 43, because 44 is a little different. I'll let you look at 44. Let's look at 39 through 44 then. Blake really wants to look at these matching ones. All right, so this is, I have the instructor's edition. I don't know if the page numbers differ. It's on page 201 for me. Is that the same for you all? We assume it is. 208?
Wait, oh, I'm sorry, I forgot to skip part.
Yeah, we're in the fundamental identities section.
Yes.
Okay, so problem like 39. So 39 through 43 are matching. So it says tan of x, cosine of x. Can we simplify that and make it look like A, B, C, D, or E? Well, what do we normally do for problems in this section? Normally, we convert to sines and cosines and simplify accordingly. Well, tangent, you can convert that to sines and cosines via sine of x over cosine of x. And then cosine of x just stays. And then simplify. Well, that's kind of convenient. Cosines cancel. Cancel, cancel. So now we have negative sine of x. And I look at the column of choices and I do not see negative sine of x.
But you can just,
Yeah, I see sine of negative x. Well, wait a minute. We know that negative sine of x is equal to sine of negative x, because that's an even odd formula. So this is kind of the theme of these matching problems. I mean, it's kind of cheating as well, because the odd numbered problems just give you the answer in the back of the book, isn't that right? So
where's the fun in that though?
yeah, let's look at 40. That one's not odd, it's even. So secant squared of x minus 1. Well, you could go ahead and convert to sines and cosines, but I see a formula. I see a direct formula. Not even a modified formula. I see a direct formula. Well, actually, it is kind of modified.
It's cosecant squared minus 1. But that's just cotangent squared, isn't it?
Yeah, so from this formula,
You would just subtract the 1.
you subtract the 1 on both sides. So really, what they're giving you when they say secant squared of x minus 1, they're telling you tangent squared.
And then convert it.
So this is a direct formula. So that's why I'm not converting to sines and cosines. I'm utilizing any formula that I have to my advantage. Then we can convert,
And that's,
because I see at least for part E says tan of x, but
this is tan.
you have tan squared. So tan squared doesn't show up anywhere, so what happens if we convert it to sines and cosines?
It's cosine. Or with sine squared over x. And then over cosine squared x.
The square just means we square both the sine and cosine.
So it's a.
It is a. I said I wasn't going to do any. Here I am doing some. Whatever. All right, cool.
We should try.
So 59. Keep looking at the emails in my inbox, and I get another one each time I flip back to the screen. I get another email. That's what happens when you teach a lot of freshmen. No offense, Blake. I mean, other types of freshmen. Let's see. So you said 59? Okay, cool. So same page. I guess this will be the last one. Cosecant squared theta. This one. Okay. We convert the sines and cosines unless we see a formula.
It's cosecant squared minus 1. That's the same formula we just did.
Well, it comes from the same.
Alright, yeah.
It's
Except for it's cosine.
so the question is, do we get a formula out of this? The answer is yes. There is a formula. For the same logic as before. So I see cosecant over here. It's not direct. So cotangent squared of theta is equal to cosecant squared of theta minus 1. And so now we see that, okay, the whole time they were just saying cotangent squared. Okay, that works out great. That's less, we don't even have to, let's see, it's cotangent. So we don't even have to expand anymore, or distribute rather. We don't have to distribute.
Now it's sine squared theta over r times, and then it's going to be cosine squared theta over sine squared theta. And then it's just cosine squared theta, because they cancel.
Yeah, how convenient is that? Cotangent is cosine over sine with the squares, because there was a square. The sines cancel. That's pretty convenient. And there's no denominators we have to clear. There's no quotients because, well, there's none.
Cosine.
And we'll call that a day, and I'll see why I keep getting emails popping up in my inbox. So call that a day.